Yes. So, hello everyone. Today we're discussing a question on EMI, electromagnetic induction. So, let us look at the question. It says that a conducting loop ABCA of resistance R naught is lying in a region of space having magnetic field varying with time as B is equals to I cap plus J cap plus K cap into e power minus 2t as shown in the figure. The arc AB is a semicircle. See, this part of the question is actually wrong. It's not a semicircle, it's a quarter circle. You can see in the diagram, right? So the arc AB is a quarter circle in YZ plane, and BC also same. It's again a quarter circle, but in the XZ plane. And arc AC is a straight line. Sorry, not arc. AC is a straight line lying in the XY plane. Calculate the flux associated with the loop and the induced current in the loop. So it's based on flux calculation and then differentiating and finding the EMF, right? But the important part is finding the flux. So let me draw the diagram for this question. So as per the question, we are having a y-axis, an x-axis, and a z-axis, and the arc AB is along this part, and then the arc BC is along this part, and after that we are having an AC here. So this is A, point B, and point C. They have given the coordinates of all of that 0 comma 8 comma 0, and this point is 0 comma 0 comma A, and this side we are having A comma 0 comma 0. So these are the points, and the magnetic field given in the question is B is equals to vector B I cap plus J cap plus K cap and into e power minus 2t. So this is the magnetic field given. They are interested in finding, calculate the flux associated with the loop and the induced current. So resistance have they given in the question? What's the resistance given? They are saying R naught, full loop, A, B, C, A. Okay, A, B, C, A, entire thing is having a resistance of R naught. Okay. Now, first of all, let us find the flux. For finding the flux, the formula that we have is actually the flux is equal to integration of B dot dA. This is the formula. Because the magnetic field is uniform, it is changing with the time, but with respect to the position, with respect to xy axis and all, it is uniform. So that's why we can consider this integration to be going as B dot A. Okay, and that means it is B A cos theta. That's it. So finding flux is kind of easy. There is no integration and all required. Now for finding the flux, we need magnetic field, area, and cos theta. So the best way of finding flux is, if this kind of a question comes where you have I cap, J cap, and K cap component, just use the component which is perpendicular to the area for calculating flux. Why? Because the magnetic flux is given as B dot A, where B is the magnetic field and A is the area vector direction. Area vector of any area is always perpendicular to that, right? So if dot product has to be a value other than 0, then the B and the A should be parallel. If the B and the A becomes perpendicular, it will be 0. So that's why, for example, if you go for this AB region, right? This AB circle, if you pay attention, this quarter circle part AB, then this is a circle in which plane? This is actually y-axis, x-axis, and z-axis. So this one is actually in YZ plane. So that's why I should be considering only the x component of magnetic field. So I'll just take which one? Bx for calculation. Similarly, if you consider this part, see, this is in which plane? This one is in xz plane. So you should consider which component of the magnetic field? You should consider only the by. And the last one, what about this one? This region. This is in the which plane? It is in xy plane. So I should be considering only that magnetic field component which is perpendicular to that area, which would be bz, like that. So if you want to find the flux, the total flux, we can say is made up of flux 1 plus flux 2 plus flux 3. What's the meaning of 1, 2, and 3? I'm considering these three areas separately because they are in different planes. So I just call it as area 1. This one would be considered as area 2, and this one would be considered as area 3, like that. So now flux 1 can written as what? B1 into A1. Cos theta value is anyway 1 because, as I told you, magnetic field and area vectors are parallel to each other. Plus this is B2 A2 plus B3 A3. That's it. Now you can substitute the value. When I say B1, it is in the which direction? B1, it's in basically X direction. B2 is in Y direction, and B3 is in Z direction. Now what can we substitute for Bx? The X component would be e power minus 2t. I cap and all not required. As I said, already I have removed that cos theta. I found the magnitude. No more further requirement of I cap and all. So this is the magnitude of the B into area. This is a quarter circle, I said, right? So quarter circle means the coordinates are given. If you look at it, this is the center of that circle. So this would be radius. A is the radius. So quarter circle area would be pi a square by 4 plus this would be also e power minus 2t, same magnetic field, into again pi a square by 4 plus the magnetic field in that b z, that will be also e power minus 2t, but this time the area is basically a rectangle, so it will become half into base. How much is the base? A. Okay, half into a, that's a square. So this becomes a total flux. A little bit of solution solving part we can do, like for example this term is being repeated, so you can write it as e power minus 2t can be taken out common, and also a square can be taken out common, and this term would become pi by 2 plus 1 by 2. If required, you can also take the 2 outside. Okay, so this becomes our equation for the total flux, but they don't want only total flux, they want also current. To find the current, you'll require first of all the EMF. EMF is basically minus of d phi by dt. Minus sign only represents that the EMF induced is always opposite to the cause of it. So minus has no significance as such. We'll just go with the magnitude of this. Okay, only the magnitude. So that will give me how much differentiation of this with respect to time. All these things are constant, so I'll be just taking the constants outside. A square by 2 times of pi plus 1, and then I have a differentiation of e power minus 2t, which should give me minus of 2 times e power minus 2t, right? That's a differentiation of this one. And again, I'm only interested in the magnitude part. There is a negative outside anyway, that will get cancelled. So finally I'm getting the answer as what? A square e power minus 2t pi plus 1. This is the EMF, but I am interested in finding the current. So current would finally become I is equals to E by R naught, because the total resistance is R naught. So that's it. So this will give me A square e power minus 2t pi plus 1 divided by R naught. Okay, so I hope you understand. It's a very simple question, a direct question. The only complication that student will feel here is what? That the areas are in different planes. So accordingly, you have to take the magnetic field component to solve the question. That's it. Otherwise, it's a pretty easy question. Okay? Thank you. We'll stop here.